So, welcome everybody. Is the sound okay? Looks good, okay. I prepare an introduction talk to my PhD thesis. I'll now start to give you a sort of a concept of what I'm doing during my PhD topic. For the presentation I'm going to give, I will also try to add a Chinese description at the end of every slide. 欢迎各位参加我的答辩典礼。所以我首先开始对我的博士课题做一个简介，然后我会用同时英文和在每一个 slide 的后面，每一个报告的后面加一些中文的解释。As you can see today, the topic of my PhD presentation is called the Systematic Search for New Solutions in Lens Design. So after the introduction talk, we will have our formal defense from 12:30 to 1:30, and there will be a diploma ceremony afterwards if everything goes smooth. And then there will be a reception at both aula, a small one, and afterwards I also organize a reception at the coffee labs next to the optics group. So everybody is welcome to join. About my PhD thesis, so title is Systematic Search for New Solutions in Lens Design. And the first thing I want to explain to you is what is actually, So what is actually lens design? As you can see on top of this picture, I put two examples of the lenses. One is a magnifier, and the other is a camera lens, which is quite common for nowadays, you can see. And I'm trying to use an arrow to indicating the engineer complexity of the optical systems. So from left to right, you have camera lens, which is much more complicated for the compared to the magnifying glasses. And if you make an analogy, because I want to also give you a direct impression on what exactly that is on the complexity. If I use an analogy of the vehicles, the magnifying glasses is something like a bicycle, and then the camera lenses is actually something similar to our consumer cars, different kinds of consumer cars. The next level, on the optical side, we will actually have a microscope objective, which we're used to zoom in to look at the microscope work. And then on the right, it's a picture of a human here, which has a diameter of 50 micrometers. So the same analogy here I use is actually a racing car. So it's of very specific usage. And the next level will be one of the most complicated optical design in the objectives, will be a photolithography objective. And these photolithography objectives are used to make the integrated circuit. Actually now we have them in your phones or computers everywhere in our everyday life. And just to give you a scale of how delicate this lens needs to be, I draw a line of 50 micrometers, which is to be seen by the microscope. And then this photolithography objective needs to achieve a resolution which is 1/1000 smaller, which is literally almost invisible on this scale. So if give an analogy of such a system, you would think about the space rocket, actually the complexity of in terms of engineering. 在这页 slides 上，我用一些图片简单的讲一下现在会有哪些光学系统，从简单的放大镜一直到光刻镜头。然后在下面这条线，想给大家一个直观的感受，对他们的工程复杂度，就相当于简单的放大镜相当于一个自行车，而复杂的光刻机镜头相当于整个航天火箭的制造。So this is about optical systems. And how do we actually do optical designs? On the left, you can see a cross-section of a camera lens. So this is nowadays pretty popular. If you go to a camera fair, they will just show you what it actually look like inside the camera lens. And then I mark the optics part with blue. So these are actually the lenses. And then also the topics in my thesis, we're focused on designing of these lenses. In the modern days, we use computer-aided design, where actually these lenses are mathematically parameterized into different variables. For example, now you see just a schematic of these optical lenses. There are the surface of the lenses, the thickness of the lenses, spacing between them, and also the number of lenses. So these are all becomes a variable for the defining such a lens system. And then the optical design is actually using, if you see in this animation, I think it's moving in the slides. So by doing optical design, we're changing one of the parameters and then trying to get a good image quality. So in this picture you see now, it's a bad image, and the goal of optical design is to achieve a good sharp image here. And by the way, that's my cat. And yeah, so to summarize, it's actually varying these variables can optimize the image quality. And then nowadays, it's heavily done by computer-aided designs. 在这一页上，我尝试来解释现在的光学设计是如何实现的。就是具体上工程上我们做的一个事情，就是把透镜通过计算机参数化，用不同的变量表征，然后通过优化这些变量来提高成像的质量。这本质上就是光学设计在做的内容。On the next slides, I would like to present you the challenges for doing such a design. So I call the title the impossible. Still use the same example. We have 9 lenses with all the surface curvature, thickness, distance, and material as variables. I list the number of variables here. And if I want to find my optimal solutions for the system, I would need to actually changing all these variables and to see which one provides the best performance, like what is presented on the right. And you have various options to change these options, which is, I put here, I use a very conservative estimation. I only have 20 variables per cases, and also just have 10 different kind of lens materials. If you do a simple mathematical combination calculation, the total available combination in this case will be 2 to the 10 to the power of 94, this number. And then I also assuming, because I have to use computer to evaluating these system designs, assuming for my system, for my computer, I can evaluate 1 million designs per second. That's already super fast computers given the current standard. You can do a simple calculation that it will require in total 7 to the 10 to the power of 35 years to do this calculation if I want to try every possible solutions. And I look in Wikipedia, the age of the universe in total is only 14 times 10 to the 10 years. And that means we would actually, I don't know, use this number of the birth of the universe to actually calculate all the possible solutions. And that's just beyond imagination. 在这页报告上，我尝试去表述，如果对于光学设计，我们需要去尝试便利每一个点进行它的系统参数的系统质量的评价的话，需要整个的运算需要超过整个宇宙寿命的年数，是非常长的。So the next slides I want to show you the possibility. So actually, with smart algorithms, that's with all the scientists and engineers who are devoted to solving the problems, we are able to bring down this 10 to the 35 years beyond imagination to only several hours. So with smart algorithm, as I indicated by all these gears here, we can reduce this astronomical number into acceptable hours. And this is actually, if you have engineers, some of you have engineer background, mainly based on the optimization techniques, development of optimization techniques, and also the understanding of physics and optics knowledges. So the thesis, or my thesis, is actually will be a tiny portion contributing to this whole cluster of smart algorithm, will be one of the many, many possible algorithms trying to make it faster. So that's the how do you position the work I'm doing during my PhD. So what actually is the work? The title of the thesis is called Systematic Search for New Solutions in Lens Design. As I show here a picture about the work we do, so how to actually systematically design the optics. The major method we're using is called saddle point construction method. It's a bit difficult to explain, but what you see is actually we are having a saddle point and then trying to, from there, to looking for different local minimum. And also in the thesis, I trying to provide an instruction, a detailed cookbook style instructions for the designers such that they can use and then do lens designs. Regardless of the complex part, if you look at the cover of my thesis, I'm also trying to express it in a different fashion. So the saddle is actually related to the saddle of the small horses. And then we always have lenses around that to indicating that's the basic structure actually we're using during the lens design. And with the simple method, we are able, in the thesis we also show, we are able to design complex systems as complicated as this one. This is a deep UV lithography lenses, which is used for chip manufacturing. Similar to the cover design, I want to indicate it with a simple method. Just following some instructions, you're able to actually design a complicated lenses indicated by these complicated patterns. So the final goal of the thesis is we're trying to provide a tool for the optical designers, and that should come into the designer toolbox, become one of the toolbox, which for the people who are designing lenses, they can use and then use them in different fields, or when they see there's an application which fits, to help them to finally improve the lens design efficiency. So that's the ultimate goal of the thesis. 所以在这页 slide 上，我尝试来解释我的课题主要做的内容。这个内容叫做安点建设法，然后它最终的目的是能够系统性的进行光学设计，然后通过一些系统性的方法，在左边的图像里面表达一个简单的系统性方法，最后能够设计非常复杂的光刻镜头。然后它最后的目的也是能够成为光学设计师里的所有的工具中的其中一个。On the next slides, I did back on some history search. So I think it's also good to really show how the topic evolved during these almost 20 years in Delft. So what I list here is the previous PhD dissertations related to the saddle point method. There are also master students' contribution from somewhere else in the world, but I didn't put here major on the PhD thesis. So you see already back in 2005, there was the first thesis by Alexander. Back then, the focus was to focus on the DUV imaging design, where he first discussed the saddle point detection for lens design. Then we have Ona as the next PhD who actually looking for saddle point detection for the mirror design, and as well as a special version of the construction method has been developed. At 2009, we have Martin, which did a really nice study on the characterization of the design landscape. So that's how it's a mathematical sort of understanding or perspective of what we are doing with the topic. And also there he proposed he mentioned about the saddle point construction in general. Well, that's where he first mentioned that. And then actually today in my thesis, I'm going a step further to this saddle point construction general method with real example and implemented in how that should be implemented in the real design tasks. And also in my thesis, you will also find some contents about the dynamic aspect of the design landscape, which for me it's a really complicated stuff. And then, but then it's sometimes if you just hold on some certain fundamental principle and techniques, you can still maneuver within this landscape, trying to achieve some nice optical design. I also indicating here in the year of 2013, actually the saddle point method, one of the version is implemented in one of the design software, which is called Optical System Design Synopsis. And the final goal, actually the use of the method is what I see it should be actually used in these design softwares, such that people or designer can really use it, learn from it, and then also feedback to the academia to do further research in a more relevant way. So today, I'm going to present this topic. In the next hour, you will have 8 committees going to ask me questions regarding the statement and conclusions drawn in this defense or this thesis. And with this, I will end my intro talk for today. So from 12:30, we'll have the formal defense, and afterwards, as I mentioned, there will be a diploma ceremony and then 2 small receptions. And today I also bring a very nice small souvenirs for you guys. It's available at the desk there together with the thesis. It's a piece of clothes you can use to wipe your glasses or lenses or whatever. But I think it's interesting. Thank you.
Ik open de zitting ter beoordeling van het proefschrift en de stellingen van Zhe Hou. De verdediging zal in het Engels worden gevoerd. I request the promovendus to go to the lectern together with the paronyms. A warm welcome for all of you at the public defense by the candidate of the dissertation entitled Systematic Search for New Solutions in Lens Design. The Board for Doctorates of the TU Delft has installed a committee to evaluate the dissertation and propositions. The committee will have a debate with the candidate in public. It's an honor to present the members for this committee, to whom I extend a hearty welcome. First of all, Professor Sinziger of the Technische Universität Ilmenau in Germany. Welcome. Professor IJzerman, Eindhoven University of Technology. Welcome. Professor Beck of Leiden University. And Dr. Kruisinga of TNO, Toegepast Natuurwetenschappelijk Onderzoek. And on this side of the table, we have Professor Hendricks of this university, from the Faculty of Mechanical, Maritime and Materials Engineering. And then we have the co-promoter, Dr. Bochort of this university, and the promoter, Professor Urbach, promoter of the candidate. Thank you all for taking part in this academic ceremony. My name is Arjen Mol. I'm professor of at this university, and it's my pleasure to chair this session on behalf of the Rector Magnificus. I would now like to start the opposition and give the word to Professor Sinziger.
Waarde promovendus, first of all, let me thank you very much for preparing this thesis, which I really enjoyed reading. and learning about the tremendous amount of work you have been doing in the design and optimization of optical systems. I would like to start with a general question on the SPC approach. As you state in chapter 3 of your thesis, there's no mathematical proof that the SPC will always find saddle points with the Morse index of 1. And you conclude from your experience, from the lot of systems you have been working on, that in general there will be only the Morse index 1 saddle points found. Can you support this thesis a little bit stronger, and can you comment what do you need to do to maybe find higher Morse index saddle points, and is it desirable to do so?
Hooggeleerd opponent, thank you for your question. If I understand correctly, the question is about the SPC, where I made a claim that in chapter 3 we will actually have a saddle point. Usually we find there are Morse index 1 saddle points, and there's no solid mathematical proof that. And my statement is that usually we actually, in the numerical experiment we conduct, there are normally Morse index 1 cases. And your question is asked in real, do we actually having, or how the use of the Morse index 2, if there's chance of finding the Morse index 2 cases, and what will be the use of these Morse index or higher Morse index cases in SPC?
Right.
Yeah. Okay. So indeed, as mentioned in this thesis, there is what we mainly did, or during my research, it's about using numerical method to look for the saddle points. And what we usually do, the approach is we do the construction based on what described in the thesis to do the derivative scan, scan of the derivative of the merit function, and then to looking for the stationary point there. And what we have tried out to how to see it's a Morse index 1, so we tried out is actually to compute the Hessian matrix there and then to look at the eigenvalue. And then it turned out for most of the cases there is actually a Morse index 1 saddle points, which we can use the nice property to go through the different local minima. And since if you look at the saddle point construction we do there, what we do is we adding two variables, curvature variables, by doing a non-element. So in the original system, it's already a minimum. And then by adding two extra variables, we were trying to construct this saddle point. The technique is to looking for the stationary point, right? So with the two extra minimum, there will be three different situations, actually. Will be either you have a Morse index 1 saddle point, or you have a Morse index 2 saddle points, or it's actually, again, a minimum. So my experience with that is by adding these two extras to being a minimum there is it's a very stringent condition, and then it requires some specific condition of the landscape, which is normally not fulfilled in practice, so that's not possible. And for Morse index 2, so we don't really have a solid proof that it will not be Morse index 2, but that's as stated in the thesis that numerical experiments showing that it's always Morse index 1, and then we use that property. And there's actually a different way to construct Morse index 2, possibly to construct Morse index 2 variables, and that is adding by adding actually more than two variables there. So we could actually have more variables there, and then you would actually have more chances of creating different saddle points with different Morse index cases. However, my argument here would be, that's also related to one of the propositions, is that using a Morse index 2 in the design may not be that straightforward as what we can do with Morse index 1, because that's a nice property we always have at Morse index 1. I know that there are two descending directions, there are two ascending directions, and then the basic structure we're using in this systematic design is use this Morse index 1 to go down in two directions.
May I briefly interrupt and
Sure.
ask, Herr Director, may we address the second proposition of the candidate?
Thank you very much, Professor Sinziger. Waarde promovendus, can you instruct one of your paronyms to read out loud proposition number 2, please?
Yes. My paronyms, could you, one of you, read about the proposition 2, please?
Proposition 2. In lens design, saddle points with a Morse index higher than 1 will not likely to benefit the effectiveness of obtaining new solutions when used in the same way as saddle points with Morse index 1.
Thank you very much, Professor Sinziger.
Yeah. You already started referring to this proposition. Maybe you can conclude, why do you think it is not beneficial to have saddle points with higher Morse index?
Yeah. So as stated in the thesis, a Morse index 1 saddle point, one of the properties is it has two descending directions, and we use this property to deviate from the saddle points and go to two local minima. However, and also in the thesis, I have stated, because for a real optical design process, there are many steps people has to, or the designer has to make decisions on what to do based on the observations. And then for Morse index 2 saddle points, one of the properties, there will be more descending directions there, where actually the complexity there is that there will be need a more advanced algorithm to actually looking at how the descending direction or deviating from the saddle point, what will be the strategy to determine another starting point in order to do optimization. And there, the control of the optimization, in my view, will be also less unpredictable. So I will not sure that it will always go to, well, if I choose a direction to optimize, if I use a local optimizer, it will always go to a local minimum. But if I have multiple descending directions, I'm not sure actually how that will be converged.
Okay, thank you very much. I would like to move on to the issue of the merit function. Of course, talking about optics design, we all know that the merit function is a very crucial aspect defining the appropriate merit function. Can you give us a more general idea about what is the best merit function when applying the SPC?
This is a very interesting question. I think merit function, at least in my view and in my experience, it really depends on different circumstances and depends on what kind of system and application we are designing. So within this thesis, we're talking about imaging system. This is usually using a merit function qualifying the quality of the image. However, there are other applications such as non-imaging or beam shaping where you have different kinds of merit functions. And even for imaging, there are a lot of criteria to quantify how good the image is. Well, I will refer to the book, Handbook of Optics from Professor Herbert Ross. You see the chapter there about imaging criteria. There's a list of 10 or 20 criteria there which can be used. Yeah, so our claim here, if you, as stated in the thesis, is also is about the merit function. The use of the merit function should be associated or determined by the application a designer needs to use, not by the method he wants to optimize. So there will be no, well, my direct answer will be there's no really a preferred merit function for SPC. The ones we have investigated in this thesis are the ones are mainly in code 5, the transverse ray aberrations. We also use, I think, in one of the chapters is about wavefront RMS when it's going to diffraction limited systems. So these are the ones which is shown in the example which can work with SPC. I think, and then talking about merit function, I think it's also already relate to optimization, because if I say to quantify the quality of the imaging, there are other ways, but those methods might not be necessarily use a merit function during the optimization because the calculation cycle is really long.
Optimization is the right word for my next family of questions.
Yeah.
I encountered two challenges related to optimization. The first was that you explicitly state that in the context of the microscope objective lenses that it is necessary to start SPC from an already well optimized solution, from a optimized local minimum. How would I know that I'm there, that my optimized result is already good enough for SPC?
Okay, so in the chapter we have actually in chapter 5 we discuss about the quality of the minimum needs to be in order to perform a SPC scanning there. So normally a minimum will be defined so within the optical ray tracing or design software. There are usually the optimization function given a certain set of parameters. You just need to run the optimization, and then at a certain, so there are the let's say the minimum increment will be determined in order to say the optimization will converge into a certain point, and check on the quality. The designer say whether it's a minimum or not a minimum. Right. However, in the research or in the study we have regarding SPC. So we have to really polish this minimum into a more well-polished minimum. So which means numerically it has to be really close to the stationary point there. So what I also show in one of the examples in the dissertation is that if a normal practice of doing around 200 cycles of optimization was probably not sufficient in order to later run SPC. And then we actually do, I think, in terms of 1,000 cycle of optimizations to have it as a better local minima in order to do this SPC scan. Mm. So the general recommendation is, indeed, when applying SPC during a optical design optimization, the recommendation will be go a bit more in the normal optimization cycle there.
Mm-hmm. Okay. And the other issue, of course, related to optimization is how to find from the saddle point, how to find the right starting point for the subsequent optimization. You elaborate on that quite a bit. Maybe you can comment on this a little bit more?
Yes. So for this, actually, indeed, because we say that we are the use of SPC is also trying to eliminate or trying to not be sensitive as for the starting point for optimization, because we claim that starting from a minimum, we can by applying SPC we can finding new minimums and then possibly forming a network to looking for all the possible minimums. Mm-hmm. However, that's when I'm looking into the details of the method. There are still within the method, there somewhere people has to make a decision on the starting point. That is indeed, as you mentioned, when we sitting on that saddle point, when you want to sort of deviate from the saddle point and then looking for the local minimum, what should be the strategy there? So that is in the thesis in chapter 5, I did the study there trying to actually plot the basin of attractions along the near the SPC saddle point landscape, and observe that, first, one of the finding is that we cannot, or it's not recommended to optimize directly on the scan line, but then possibly to do a other direction, probably orthogonal to the scan line there. And there's also some empirical, based on our experience, what the distance should be in order to step out from the saddle point construction. So these things, I think in the thesis I've mentioned about roughly what will be the ratio compared to the original curvature. But I have to say that the high level, the principle would be you don't want to step too close from the saddle point construction, such that you still remain within the vicinity of the saddle point. And the designer neither want to step too far away from the saddle point, because that will have a chance make you dropping into a different basin of attraction. So.
Okay. maybe to come to the end of my questions.
Sorry,
maybe
Professor Singer. The time is,
okay.
is up. Are you satisfied with the answers to your questions so far?
I'm satisfied with the question, with the answers. Thank you.
Okay, thank you very much. Then I invite Professor IJzerman to continue the opposition.
Waarde promovendus, I would like to congratulate you with this nice piece of work. I think lens design is originally more an art, craftsmanship than a science, and your thesis brings a little bit structure in that field and gives some directions how to make it more a scientific approach than a craftsmanship approach. And that's very needed in the industry, I can tell you. So I have also a few questions, and I would like to start on page 51, section 4.3, where you are designing a pinhole system starting from a single lens, as the title reads. And this paragraph describes several steps to come to a lens system. And I would like to understand those steps a little bit more in detail. So you say you start from a flat plate and then do global optimization to come to your first lens system, which is illustrated in figure 4.3 on the top left side. My question is, what kind of global optimization did you use for this? And why did you choose this approach? Because I can design a single lens surface in different ways.
Hooggeleerd opponent, thank you for your question. So the question is about what I'm now showing also now is about the page 15 where I design a pinhole lens. And then here I actually in figure 4.3 where I show actually from very simple single lens cases and then how to finally converge in or by applying certain design steps and how to go to this final results. And the question is, why do I use global optimization at the very beginning to design such a single lens?
Yeah, correct.
Yeah. So my answer to this is actually, there are multiple ways to design a single lens indeed, and then there are actually, based on designers' experience, they will start from certain curvatures and then do optimizations there. And here, because in my research, I think at the beginning it's always assuming that there possibly can be multiple minimums, so I don't know if there's more than one possible design solutions. What we can see here is indeed, after applying global optimization, it converges into one of the solutions. That's where I start from my design. However, if I could find more than one designs, I would actually having multiple paths to continue with my next design stages.
That's precisely my point. You might start with different points. You don't know.
I don't know, indeed.
Okay.
Yeah.
And then you add, and all these steps are described in the text. So then you say, I add one lens, zero element at the end. And you do your local optimization with SPC. But what if you would add something on the front? Would you obtain the same result? So that's the one with a merit function of 164.82. So it's the second picture.
So, okay. So it's the second picture here. The question is about now in the description here, we are mentioning that we are adding a non-element for doing SPC at the last surface to run through the SPC and then coming to the next system, right? And then the question is, what if I do a SPC at the different surfaces? So the answer to that is indeed there are actually multiple positions we can do SPC, and that is in my thesis, we didn't really extensively study that. And then in some of the occasions, we more like doing a brutal force method of, or using some sampling within the lens designs to picking front or end surface of each element, and as well as also the middle of the surface to do the scanning. I think the showing of this example, now I don't remember by heart if I did actually that search at the front place. Probably I did, and then it turned out not very succeed. But the purpose of this graph is actually trying to showing the step how we can achieve a final solution with the method. Mm-hmm. But indeed, this is not covering the whole possibilities within this design landscape.
Yeah. And of course, in that same design, you mentioned that for the two duplet minima, there's also another one which is less favorable in the text. yeah, which is the last line in the second paragraph. And you say that one disappears if you replace the effective focal length from 3.5 by towards 3 millimeters. So what does that tell you about the quality of your minima? And can you define quality?
So, okay, so we actually from the process would be from the first lenses. If we do a saddle construction, we can achieve 2 different systems. And then, well, as indicating in the graph, you can already see the merit function of the 2 cases. The second one is 10 times higher than the first one. And here I would also say, normally what lens designer, when seeing this second lenses, you already see this surfaces or almost a cemented surface, looks very stressed. So it's indication, I think that requires some design experience. It's indication this lens is already at the edge of traceable by the rays. And then any sensitive movement or deviation from the current configuration might result as a ray failure. Therefore, the system is failed.
Yeah, I agree. Yeah, I think that's the reason why it disappears. But of course, that means you need to do some manual checking, or can you do that automated to see if a minimum is a favorable minimum? Because you add now engineering criteria, and that's the art, the craftsmanship I was talking about.
Correct. I think that's indeed a good point. And well, it's not discussed within this thesis, but I would say there are literature actually about how to qualify the fitness of a lens or the relaxedness of a certain optical design. We didn't implement those metrics in the design work, but definitely there are existing literatures describing how relaxing or what is the chance a certain system will fail.
And then you move on by adding again, but then on all surfaces, 0 elements, and you end up with 4 potential optimal solutions. And then I'm a bit surprised because you do optimization, and then I see the merit function of one of those is higher than the merit function of the one with only 2 lenses. So can you explain me why this can happen? I'm minimization, I'm adding an element, and then it doesn't improve, it becomes worse. Yeah.
So I think...
so that's the one with 182.9, the one on the right. Yeah, that one is higher than the 164 that you started with.
Yeah, so the question is about now from this step to the next step, adding 2, 3 lenses. So adding more freedom is supposed to give me more degree of freedoms to optimize my system, which means a better chance of improved performance, which you can see actually in the 3 of the variables which are showing here. However, one of the system is actually showing a much higher merit function compared to the second lens. The question is why this situation can happen. My answer to that is first, well, I would say a similar point compared to the doublet to the left, you would again also have a very stressed situation of that case.
But also there, why?
So the method. Well, I think my understanding for this question would be in the third order, in this triplet design landscape, there is still such a solution exists, and by using the saddle point construction, somehow we connect to that solution, and I don't see no, well, so that's just the property of the design landscape. There could be such a bad solution exists, and then that's exactly the solution people want to avoid and then leave.
Okay, I understand that it exists, but I'm surprised that you can find it, because I would think, naively, if I start with a saddle point and I'm walking into the descent direction, I should end lower than where I started. And also intuitively, if you add an element and you are trying to descend, then you should also end lower.
Okay, so the question is actually, by adding the saddle point, we are remaining the same value of the merit function, right? By further optimizing to that, that is a step, it should be going lower. Here there is actually mentioned in the thesis is about the constructing of a saddle point is by adding a non-element. So that's an element without any thickness. And now actually, what you see in the triplet, there is also discussed, there are a step after finding the minimum. The local minimum is a non-element and minimum. That's the first step. And if I don't have the data here, but if I retrieve that one, I can guarantee that that merit function is definitely smaller than the 140-64 we see here. But then the next step, we have to increase the thickness of the lens to become practical, and that actually has a chance of increasing further.
Yeah, so that's in the hidden step of optimization.
Correct. Yeah.
Meneer Director, is there time for another question?
I'm afraid we're running a bit tight in time, but are you satisfied with the
I'm
answers?
satisfied with the answers.
Thank you very much, Professor IJzerman. Then I kindly give the word to Professor Beck to continue the opposition.
Thank you very much, Meneer Director. Vade promovendus. It was really interesting for me to read your thesis. I'm coming from a different perspective, namely the perspective of global optimization methods. And one of the questions that struck me as maybe a naive question is, can I design these systems completely from scratch without any expert knowledge, maybe?
Hooggeleerd opponent. So the question is about, is it possible to design the optical system without any expert knowledge?
Yes. Yeah.
Yeah. So I would say yes, depends on what you want to design. So because there's a wide range of optical systems, I think the main goal of this thesis is also showing that for simple system, actually nowadays the global optimization tools is already quite powerful. And by setting up the right memory function, actually the optical system is actually just able to, or the software just able to optimize into a system which is workable. However, for more complicated ones, there are more techniques needed. So I would say nowadays for simple system, that's definitely possible.
I understand. So my naive approach would be, again, not knowing the domain, let's just optimize for all possible dimensions. Like we go for 2 lenses, 3 lenses, 4 lenses, 5 lenses, and do a fixed dimensional optimization and then compare the results, rather than what you essentially do is increasing the dimensionality by 2 every time, right? So if I had unlimited computational power, which I don't, but if I had, could I just run, let's say, 20 parallel optimizations of a fixed dimensional optimization representation?
So the question is about if there is unlimited computational power,
or enough,
right? And then can a person just run like with all the variables there and then achieve a certain system, right? So my answer to that is, if there is a sufficient computational power, you will definitely, it's possible definitely to get a solution, or possibly more than one solution, but then the designers still have to choose actually which is the one you needed. So you need decision making from the person, and that's
sure. But if I make the merit function comparable, then the decision is easy, right? So less lenses with the best, the smallest number of lenses, I suppose, because making more lenses seems to be more costly, maybe. And then just let's see whether the merit function is comparable.
Yeah. So that's indeed about the how people define a merit function, since it's a very applied engineer or study work. If the designer, or if today a person wants to just to optimize the focal point or a certain very simple merit function, I think that's nowadays definitely possible. There's even sort of guided steps in the design software to help people do that. There's even actually someone did there are literature about applying deep learning neural network into lens design, where people actually make a web-based interface. So people just need to put in the parameter what he wants, and then that interface will directly providing a lens design outcome.
Because the neural network would be able to predict what the lens system should look like.
Correct. Yeah, that is already trained based on literatures. Yeah.
When reading your thesis, I speculate that many constraints are hidden in the merit function in the penalty terms, and that some of those constraints are conflicting. An obvious one is, I understand with more lenses I can easier reach my goal, but of course the system becomes more expensive. So these are obviously 2 conflicting objectives. But there might be more. did anyone ever consider this as a real multi-objective optimization problem where conflicting objectives are considered, not put into the same merit function, but actually the whole Pareto front has been tried to approximate?
Yeah, so the question is there, study about parental optimization or multi-objective optimization in order to improve the comprehensive performance of optical system. I think there are definitely literature about that. So there are what my focus in the thesis is about how to improve the performance, imaging performance in this sense. However, to really have an optical system, there are costs need to be considered, and a big part is about tolerancing. So how good it can be manufactured. So I've seen actually literatures about combining these different objectives into merit function in order to, let's say, to generate a manufacturer-ready system.
So we have good reason to explore that direction too. Herr Director, I would like to ask a question about proposition number 3.
Thank you, Professor Beck. Madam Promovendus, can you instruct one of your paradigms to read out this proposition?
The type of optimizer used is essential for the optimization outcome.
Thank you very much, Professor Beck.
Madam Promovendus, I find this a bit of a trivial statement because you are missing a second component in this proposition. Can you imagine which second component I mean?
So, thank you for your question. The proposition, I think here I put it actually quite simple, stating the type of optimizer will be essential for the optimization outcome.
Yeah.
And this is actually, there need context to be provided. So what is the definition of the optimizer, and what is actually a optimization outcome there? And
yes, but you are a little bit misled. So the question is really about the objective function, because the other thing you need is the objective function. I think you could say the type of optimizer and the objective function together are essentially for the optimization outcome, because that's, after all, I think the key thing that we are looking at, that what is the structure of my problem? And I think this is a very interesting indication. There is something in your problem structure that makes it apparently interesting for this type of optimization approach, where you add 2 dimensions, then you have for sure 2 new local optima that you can find from the saddle point, which is a very interesting problem structure. Could you imagine that your optimization approach, your new optimizer, could be a general purpose optimizer for general nonlinear global optimization problems? Or is it extremely specific for this problem structure?
Okay, so the question is about, will the SPC method can it be generally applied to other kind of optimization problem?
Exactly.
Yeah. So my answer to that is not really, because that's also what I've been busy for my PhD, trying to find a different way, actually trying to see how it can be applied in other cases. The learning, at least from my research time, it's highly dependent on the structure of the lens design landscape. So that's where we find this method is effective, and then we can use for systematic design.
So there are specific characteristics of this landscape, and that's why in my field there's something like landscape analysis, where we are trying to establish a relationship between landscape characteristics and the right optimizer for that type of landscape characteristics. I think you've done a very important piece of work here by identifying landscapes that have certain properties and a very good optimizer that is actually useful for these properties. I'm not sure whether I'm at the end of my time.
More or less, yes. Thank you. Thank you very much for your opposition. Then I invite Dr. Kruijnziga to continue the opposition.
Padre Promovendus, I also enjoyed a lot reading, studying your thesis. And I think it's a good summary of what is actual happening in the field. And I have a couple of questions to see what is your view
on those topics. And first of all, I would like to go to chapter 6, in which you have the simultaneous multiple surface method. In the method, in all the examples that you describe, all the surfaces in the system will be made aspherical. Now, of course, that can be done, but an A-sphere is more expensive. It has more parameters. That's why we use it. And as a consequence, it also has more tolerances. And especially a double A-sphere, so a lens with A-spheres on both sides, is in terms of tolerancing not a very good idea. So how could you, using the SMS method, to look in the system and find the one or two surfaces that are most efficient in turning them into A-spheres? Can you comment on that?
Zeer geleerd opponent, thank you for your question. So the question is about the application of simultaneous multi-surface method and A-spheres. And then the question is how can I comment on using SM method to determine what is the optimal position for a sphere in the optical system?
It's not necessarily, you need not necessarily be limited to the SMS method, but more in general, how could one find the most efficient surfaces to turn into a sphere?
Yeah, so then, okay, so the question is in general what is strategy to aspherize surfaces within system, right? Okay. With this question, actually, first about the SMS method I studied in chapter 6, it's indeed purely the 2D versions or the versions we have here can only construct aspheric systems. It's still symmetric, but then only on aspheric surfaces. It does not provide any insights on where to aspherize the surfaces. One of the variations is the people can actually having a already spherical system and then decide where to aspherize and then using SMS to start constructing those aspheric surfaces. That's a technique, but it does not provide insights on where to do that. Personally, I cannot really, or I don't know any techniques on how to aspherize the cases. What I can, what my knowledge would be there are certain ways for the optical designer to look at the aberrations of the system, to examine the elements on the surface contributions of each element, and then use that to actually determine where to aspherize, and then to see whether it improves or not. So that's one of the things. However, I remember several years ago, I also see a literature from a Japanese author that is about how to determine the aspherized surfaces in the optimization. So I'm not an expert, but high level, because determining where to aspherize, that's more like a discrete optimization problem. So on high level, he actually converts a discrete optimization problem into a continuous optimization problem, such that he can use the nice optimizer within all these continuous scheme to run this one. So there are some certain optimization tricks can also be applied.
Okay, thank you. And a question connected to this, how would one use the SPC method to introduce A-spheres in an optical system?
Thank you for your question. The question is about how can we use the saddle point construction method to introduce A-spheres in the system. So the essence of the SPC method is trying to introduce a non-element within the system, and this non-element shouldn't change or shouldn't bring any real physical change in the original system, which is already a local minimum. In the lens design cases or in the spherical design cases, we do that by introduce two curvatures, or non-elements which are having identical curvatures and zero thickness between them. So I've thought about how to do it with A-sphere. So idea on my mind was actually to introduce, because as far as spheres are adding extra orders or terms to describe the surface shapes. So if there is a smart way to introduce more order of terms without changing the original shape of the original surfaces, probably that's a direction actually to go for, looking for using apply SPC in the spherical cases. However, I think I probably did some study back then and didn't find that's a really effective method to do that. So it was not a really promising direction back then, I concluded.
Thank you. And the next question is about the, let's say, the measure for optimization efficiency that you use. So you treat in your dissertation quite a number of ways. You study them for optimization. So one of them is the global synthesis that is built in Global Optimizer in Code 5. In the method of SPC, you discriminate between zero thickness glass and zero thickness lenses, zero thickness airspace. And then, of course, there is also the various positions where you can insert the null element. And then finally, there is a netmin, which is also looking for subtle points, but using a different way, using the Hessian matrix, etc. But I think those ways of optimization are not very comparable. So you use the measure of efficiency, the number of cycles that you need to come to the best solution. I would say a better definition would be the number of man-hours that are needed from the optical designer, so the degree of user intervention that is needed. So if I start a global synthesis optimization, let it run overnight or over the weekend if necessary, then it does a lot of cycles with almost no or virtually no user intervention. Can you comment on that?
So the question is about how I define the efficiency, actually about different optical design methods, and then the suggestion is a more proper definition should be the usage of man hours rather than computer or robot hours there, right? My answer to that, I think that's, well, my understanding to that question is also about the time used in or taken by the computer or even optimization cycle is actually one of the important parts for the designers. Why do I say that? Because that's also during my experience I have compared two methods. One is the saddle point detection, the other is saddle point construction, where we see the saddle point detection, that's a more tedious method which takes much longer computational time. And the ground I'm taking is that finally that's the decision that the designer has to make at a certain point after seeing the results from the optimization. And we would actually benefit, or the designer would benefit a lot if there's a much faster feedback cycle. So it makes a difference if I see my results in 5 seconds or in 5 weeks. So during that interaction times, it makes a difference.
Fair enough. Do I have meneer de...
I'm afraid not. Oh, sorry for that. Are you satisfied with the answers?
Yeah.
Thank you very much. Then I kindly give the word to Professor Hendricks to continue the opposition.
Waarde promovendus, first of all, my congratulations with the nice thesis about the SPC method. I've read it with a lot of pleasure, but I have some questions, and especially I want to address questions concerning chapter 5.3, where you have an ultraviolet microscope dry objective lens, which you want to improve with your method. If you go to figure 5.10, then if you look at that, you have all kinds of lenses, and one of the problems that you are addressing is, okay, where should I start inserting the additional lens? And by doing so, you look at spherical aberration. But this design is also something which has a field of 0.1 millimeter. So that means that at the field, you also will have a significant amount of coma. And in the figure of 5.10, you only show, let's say, the contribution of spherical aberration. If you incorporate, let's say, the coma contribution, would that change, let's say, your opinion on where to insert the additional lens?
Geleerd opponent, thank you for your question. So the question is about the system I studied in chapter 5, which is a microscope objective, where I try to actually combine the usage of SPC together with the designer's knowledge, conventional designer's knowledge. And here in this study items, I basically saying that by using SPC, we have the more chance to provide or provide more design candidates for the designer to make decision upon. However, I also mentioned in the thesis that the SPC will not inform the designer where to insert the glass. That is combined with the designer's opinions or experience. And for your question, I think that's definitely valid because as I mentioned also, these strategy or determination of where to insert glass to improve the system performance is really depends on different designers' experience. So the one I was collaborating with for, actually someone is looking at the property of spherical aberrations of these objectives. From his study, that's really focused on the spherical aberration part, and then that's where he concludes a certain group distribution of the spherical aberration, where group in the middle and the front is actually correcting for the one introduced on the rear. So in this case, we come to the conclusion of where to do the insertion. If there is comma presented, if there's also analysis on comma, that can alter the decision, because we will take into our matter function not only spherical aberration, but also spherical aberration and comma together.
Okay, thank you for your answer. So when you look more at the design, would there then be of course the SPC method doesn't tell you where to put the lens, but do you have some suggestions on how to, or that might be, let's say, worked out in general? So some guidelines on how I should use that, so where to put the lens?
I think the question is still how to improve the comma there, if you say. Okay. So, well, I myself is not really experienced in all these designers' knowledge. That's also in the study is really trying to, using a method which people can base on as less as possible on the designer's knowledge. If I make a comment here regarding improving on the comma, so from my knowledge, I think bringing the symmetry in the system will actually help improve the comma. So I would then think about how to create symmetric structure, so which is actually from my middle or front, or bring a symmetric structure with on both sides of my aperture there. So if I would actually try to balancing the lens on both left and right of my aperture, and then start inserting lens on the other side, which is less lenses.
Okay, thank you. And then you start, let's say, with designing, and in one way of what you are going to do is that you increase the NA of the objective on the next subchapter. And in doing so, you insert lenses and then look at the new design types that come out. And then finally, in figure 5.13, you show an overview of what you have found, let's say, as results. And if I compare all these designs, then let's say 4A in your table turns out to be one of the best designs that come out of this endeavor. However, if I compare these lenses, they don't have all the same length, etc. So they have different dimensions. So apparently not all the constraints are kept the same in the design. Has this influenced, let's say, the result in this respect?
So the question is about the picture I'm showing here, where the numbers are indicating where the insertion of the lens is, where we do SPC, and then the total amount of solutions we see here is actually the amount of available candidates for the designer to go into the next step of the design. And indeed, as you mentioned, at this stage we are only using maybe the effective focal length and the image quality or one of the constraints, but not considering the total length of the components there. So I think that is somehow in this analysis indeed which is not added. And I think my view is depends on the real application. If there's indeed such a constraint, then the finding also from the SPC is that when we applying the method, we want to make the method or make the construction less constrained as possible, such that there are more chance to provide more candidates. And these constraints can actually be applied in the next step. So if indeed we want to apply such a constraint from out of these 20-some candidates, the designer can constrain the system to do a further step to evaluate the performance on that.
Okay, and if you would have, let's say, a method for that are available, let's say, in all kinds of lens design programs, like brute force optimizations, have you tried that to compare that and to see if that would result in better designs that you have found with the SPC method?
So in this example I'm showing, we didn't try to compare with other methods. So in the formal chapter, where in chapter 3, where there are more simple systems studied, or in the beginning of chapter 5, I think there's also system of the, for example, if I'm showing this network of a pinhole lens consists of 2 ports. So all these methods we have compared with indeed global optimization algorithm, which is global synthesis in code 5, to see indeed are we missing with SPC any new solutions. And the conclusion there was actually basically all the reasonable system found by global optimization method that is also found by SPC. What I mentioned reasonable because of how you set up the mirror function for global optimization can generate some on physical systems there. And the other cases is about the for complicated systems. So here it's still a reasonable amount of outcome generated by global optimization. For complicated system, which I mean more than, or the lithography lens or more than 10 elements, we didn't really do that kind of comparison study because the effort of analyzing those results from the global optimization is also quite tremendous, because then designer has to go through all of them. And that was also not one of the study during my cases.
Okay, thank you.
Okay, thank you very much, Professor Hendricks. And I kindly give the word to Dr. Bochort, co-promoter.
Waarde promovendus. I would like to focus on some issues which you have just treated, but where perhaps some continuation of the work would be interesting. So for instance, when you have discussed your very complex systems, you have said that you have encountered situations where the original local minimum has to be polished with many, many cycles. Now, if you look, for instance, at figure 5.23 on page 98. Now, if somebody would like to continue the work which you have started, could there be a more practical solution than optimization with many cycles in order to prepare the starting point?
Zeer geleerd promoter. So the question is about is there a more practical or suggestion on only more than optimizing more cycles in order to proceed with SPC? Is that correct?
Yes.
Okay. So at least from the finding of my thesis is that the local minima has to be polished sufficiently in order to properly do the SP scan, because if we are not starting from a local minimum, the scan of the derivative will not likely to find a proper saddle point. And then the outcome of that is actually, well, the starting point of the saddle point will just well, we will not find that saddle point basically in that situation. So the practical recommendation for me would be when implementing such a method in lens design software with SPC, well, we have to put some criteria to evaluate how good that local minima is by calculating the let's say the first derivative or something, trying to indicating that's already a good local minimum. So that's by implement some smart strategy within the whole tool package.
What you say is correct. However, I don't think that many people would be prepared to optimize with a very, very large number of cycles if you have a lithographic lens with 100 variables. But if, for instance, you look at figure 5.23, if you look there, you see that the changes introduced by SPC are pretty localized. Would it be possible, for instance, to get the same kind of solutions with a smaller number or by reducing the number of variables?
Thank you, Madam Beadle. I request the promovendus and the paronyms to take their seat back in the audience again. The committee will now withdraw for further deliberation in the committee room, and this session is adjourned. I reopen the session and request the promovendus and the paronyms to stand in front of the committee. Het College voor Promoties van de Technische Universiteit Delft, vertegenwoordigd door de hier aanwezige commissie, heeft, na kennis te hebben genomen van uw proefschrift met stellingen en na uw verdediging daarvan te hebben gehoord, met inachtneming van het bepaalde in de Wet op het Hoger Onderwijs en Wetenschappelijk Onderzoek, besloten u de graad te verlenen van doctor. Ik verzoek de promotor door het College voor Promoties als zodanig aangewezen zich wel van de hem opgedragen taak te kwijten.
Uit kracht van de bevoegdheid bij wet toegekend aan het College voor Promoties verklaar ik namens dat college, hier vertegenwoordigd door de rector magnificus en de overige leden van de commissie, bij deze u Zhe Hou te bevorderen tot dokter en u alle rechten te verlenen welke aan de dokterstitel zijn verbonden. Ten bewijze hiervan overhandig ik u het diploma dat u het recht geeft de titel dokter te voeren. Ondertekend door de rector magnificus en de promotoren en voorzien van het zegel van de Technische Universiteit Delft.
Gaat u zitten.
It is now the promoter's privilege to be the first to congratulate the young doctor. Professor Urbach, the floor is yours.
Dank u, meneer de rector. Dear Dr. Zhou, dear Zhe, I'm happy to finally have handed out the PhD degree to you. You say in your thesis, and I quote, "It has been a long journey. Some people say that a PhD can be a lonely journey. However, I would not be able to undertake it all by myself." Now, a PhD project always has had, and in my opinion still ought to have, the character of an exam which one can pass, but which one can also fail. The outcome of real research is to a certain extent unpredictable. And since, as a PhD, one has to produce most of the results oneself, one can feel really lonely when things do not go, in particular when things do not go as wished. And I very well remember that from my own PhD. Now, at the expense of considerable bureaucracy, the graduate school tries to make the track towards a PhD more predictable and aims to increase the success rate. The graduate school does not exist long enough to judge whether it is successful in doing this, but it's rather obvious that for some PhD projects, the ones that have difficulties, certainly not for all, but the ones that have difficulties, the implemented policy by the graduate school may substantially reduce the research character because it reduces unpredictability, and also it may lower the standards. Now, you started your PhD before there was a graduate school, and very decently after 5 years, you moved to ASML. The work was basically done. Now, Florian and I did not doubt that your research results justify a PhD degree. You still had to finish writing the thesis, in particular the introductory chapters, but that seemed possible within a year. Now, the reason that it took so much longer to celebrate this happy ending today is that you had doubts about how valuable your results are, and that therefore you lacked the motivation and the energy to finish the thesis. Therefore, some time ago, I asked Joseph Braat to contact you. And in your acknowledgement, you say that you are deeply indebted to Joseph for valuable advice and for providing motivation to finish the work. And I also want to thank here, although Joseph is not present today, I want to thank Joseph for his great help in achieving this. As is obvious from the standard book of almost 1,000 pages on optical imaging, which Joseph has published in 2019, you could not have obtained any better support than from him. By the way, in your thesis, you did not refer to his book. I assume you have it, but if you don't, you should immediately buy it, because any serious optical designer should have it. You can tell me confidentially after what is the status. Now, Zhe, about your career in Delft. You came from Zhejiang University, Hangzhou, a famous university in China, and you received a scholarship to join the European Master Track Optical Upside Tech, as it was called in those days. And it was coordinated by the Institute Optique in Paris, and the optics group in Delft was one of the 7 academic European partners of this international master in optics. And your master thesis work in Delft with Nandini was very impressive experimental work to determine diseases from spectroscopy of exhaled breath. And it led to a publication in Optics Express. After your master here in Delft, you became one of the 12 PhDs in the European project Adopsis. Also with 7 academic partners, in this case Delft was the coordinator. Because of your experimental skills, I was surprised that you said you wanted to become an optical designer and that you therefore choose the topic on lens design for your PhD. But it shows your broad interest and also your broad capabilities. Now, every PhD in Adopsis had to do 2 short 3-month internships, one in an academic partner and one in a company. And you went to the group of Professor Mignao and Pablo Benitez in Madrid, and later to the company Datalogic in Bologna, working on barcode readers. Since you are a serious and very pleasant person, it was no surprise that you had many fruitful collaborations within Adopsis. Apart from the scientists just mentioned in Madrid and Bologna, you also had an outstanding collaboration with top optical designer Professor Irina Lifshitz from ITMO University in St. Petersburg. She made many good initial designs, which you then improved using your methods. And this has led to 6 conference contributions and publications altogether. Normally, Professor Lifshitz would, of course, be present here as a member of your PhD committee, and that does not mean that I would like to miss any of the other members that are present here, of course. But now, since the politicians again are interfering with our life in such a dramatic way, so that we, as scientific community, cannot decide anymore with whom we can exchange information and so forth. It was unfortunately not possible to have Professor Lifshitz here in Delft. Now, to end good is all good. And it was really a pleasure to have you as PhD in the group. I congratulate you, your parents, your girlfriend, and wish you all the best in your personal and professional life.
Learned Dr. Hou. You now have the right to use the title of doctor. Your doctorate means that society can rely on your judgment, that you will act transparently and communicate independently about your results and the social relevance of your work. In other words, your doctorate implies that you will uphold scientific integrity. I wish you a great deal of wisdom and prosperity with your new degree. On behalf of the Board of Doctorates of Delft University of Technology, I congratulate you and your family on earning your doctoral degree. Dr. Hou, you now may return to your seat together with your paronyms. Ladies and gentlemen, I thank you very much for your presence, and I hereby close the academic session.